In this video, we will present the conventional amplitude modulation. This modulation is also known as the double sideband modulation with carrier. And this is because in the analytical expression of the modulated signal, S of t will denote the modulated signal, we have two components. A carrier with a fixed amplitude, phase, and frequency, and a second term with the product of the modulating signal, m of t, the information that we want to transmit, and the carrier. Therefore, the cosine now is multiplied with this term, the carrier amplitude times 1 plus the modulating signal. The ideal situation is to have this term always non-negative, greater or equal than 0, because in this case the envelope of the modulated signal is equal to this term, which is proportional to the modulating signal. And an envelope detector will allow to recover the information. In this picture, we have an example of a given modulating signal, m of t, the information, a carrier, a cosine with fixed amplitude, phase, and frequency, and here we have in green the term that now is multiplying the cosine, the carrier amplitude times 1 plus the modulating signal. If this is non-negative, as it happens in this example, if we plot the modulated signal, we have this signal, and the envelope is proportional to the term that is multiplying to the cosine and is proportional to m of t. If we use an envelope detector, the information, the modulated signal, can be recovered just by removing the mean and scaling the output of the envelope detector. However, if this term is negative in some time intervals, an effect happens that is called over-modulation. This happens when the modulating signal is lower than -1, and in the time intervals with this situation, the modulated signal is inverted with respect to the carrier, and the envelope becomes proportional not to this term, but to minus this term, which is proportional not to the modulating signal, but to minus the modulating signal m of t. Here we have the same modulating signal that in the previous example, the carrier. Now the carrier amplitude times 1 plus m of t is negative in this time interval. If we plot now minus this term, we have the curve in red, and in blue we have the modulated signal, s of t. In this time interval, we can see that the modulated signal is inverted with respect to the carrier, and if we obtain the envelope of the modulated signal in this interval, it is not proportional to this term, where we have something proportional to m of t, but is proportional to this term, when what we have is proportional not to m of t, but to minus m of t. And therefore, it's very simple to see that with an envelope detector, now we cannot recover the modulating signal. The solution to avoid overmodulation is relatively simple. We only need to normalize the message, the modulating signal m of t, and we will introduce a new parameter that is called the modulation index, parameter A. First, the modulating signal is normalized by dividing it by the range of this signal, the maximum value of its modulus, and then the normalized signal is multiplied by the modulation index A. And therefore, what we have is that the modulating signal with modulation index A is equal to the modulating signal times the modulation index divided by the range of the signal. And this signal now has a range between minus A and plus A, between minus and plus the modulation index. Therefore, to avoid modulation, the modulation index is constrained to be greater than 0 and at most 1. Finally, here we have the final analytical expression for the modulated signal of a conventional amplitude modulation with modulation index A. M of t has been replaced by ma of t, and we have the carrier plus ma times the carrier. We have the cosine multiplied by the amplitude of the carrier times 1 plus ma of t. Now, with the introduction of the modulation index, the range of the term that is multiplying to the cosine is the carrier amplitude times 1 plus a and the carrier amplitude times 1 minus a. That is always non-negative if a is lower or equal than. For instance, here we have an example for a modulation index equal to 0.75. The amplitude term that is now multiplying to the cosine is never negative, and the modulated signal has no overmodulation. Overmodulation will only happen if the modulation index is higher than 1, because in this case we can have a negative interval for this term, and in this case we'll have overmodulation here. But remember that the modulation index is constrained to having a maximum value of 1 to avoid intermodulation.